begin by just showing just one screen for the lemma to how it goes. Then okay, the other things are also there was yesterday there was I mentioned somewhere in the middle of the talk that I was missing one square integrability of k-finite Fourier coefficients of the theta lambda. That's one topic. Only some ideas will be presented. So it involves a study of the asymptotic behavior of k-finite tempered eigenfunctions about which I think you're also going to talk, right? Asymptotic behavior, okay. And then integrating over conjugacy classes, short space, cusp forms. So these are some other things we'll go through today. So let me begin with that missing factor. This is what you see here is a missing factor. So that factor was missing yesterday. Okay, so this, my God, my sons seem to remember the bedtime story I used to tell them when 40 years ago when they were very young. So that is the second one. It says, Lee Group's happy birthday. Next one. Oh. Next slide.
Today is the birthday?
Tomorrow. Okay, so I have to give you some idea of what is involved in the proof of the lemma 2. It involves, what was lemma 2? Lemma 2 was an existence statement. There was the dimension of the space of that d nu epsilon. It is equal to the number of cosets of the smallest well group in the biggest well. That is the statement. So for that, what we do is, or what Harishchandra does, is in the d nu epsilon, he takes a nu. For that nu, he defines an element. It's he goes to this element using the killing form, okay? Using the killing form, and then looks at multiplying by square root minus 1 and then taking well group, translates of that element for all elements of the well group. So the orbit of this under M is closed in the Lie algebra. So in the Lie algebra of M, that orbit is closed and it admits an invariant measure. It admits an invariant measure. So it regarded as a distribution. Regarded as a distribution on M that is tempered and also the Fourier transform of that. The Fourier transform satisfies these differential equations. The tilde there, the twist by tilde is something you can ignore now. It just means shifting by half the sum of roots, half the sum of positive roots. So it satisfies the required differential. So you have a tempered distribution and it satisfies the required differential equation. So we have so many corresponding to each element of the biggest value. But if two elements of the while group are the same coset corresponding to the smallest while group, you are going to get the same distribution. So that is the idea of the proof of the lemma. Now we will equations with respect to the action by the center of the enveloping algebra.
And these distributions also have some growth properties. We formulated two lemmas about this space of distributions. Our main objective was to assume these two lemmas and apply them to arrive at the construction of the discrete series characters, that is, the distribution characters attached to discrete series representations. We finished that in the last lecture, and we completed the proof of lemma 1 also. The lemma 1 is a uniqueness property. If the distribution is 0 on the compact orthon, then it is 0 everywhere. Today we will take up the proof of lemma 2, which is an existence property. So let us recall what is a tempered distribution on an open subset of a real Euclidean space. So take a test function and differentiate that test function with respect to a differential operator with polynomial coefficients, and take the upper bound of the absolute value of the slope function. And so they define semi-norms, and thus they define a topology on the space of test functions. So a linear form which is continuous in this topology is a tempered distribution. Whatever we have done so far, that is the construction of.
After that, some slides were missing, and that is what I showed you. The proof of lemma.
The characters theta lambda has to be eventually connected to square integrable representations with matrix coefficients. That is the so-called discrete series representations. So what we have to do is say how these theta lambda distributions are connected to the distribution characters of the discrete series representations. This is a very delicate task. Along the way, we encounter a lot of terminology. So here is a curtain raiser to the long list of objects we are going to encounter soon. Okay, the first orbital integral. Take the joint orbit of a regular element B of a Cartan subgroup L. On this orbit, we integrate a given function f, and this ff is recorded as a function on the regular set L prime. As a function on the regular set, it has a very nice behavior, but how it behaves on the singular set is a delicate problem and depends on the Cartan subgroup. We will see more about it later. I shall us two notation for this orbital integral, ff with a back prime and another one without the back prime. The difference is that differentiation by an element of the center of the envelope algebra has a better formula for one of them. Then another notation for a parabolic subgroup Q and function f of G, this function fq on the reductive part of Q, in the Levi decomposition by integrating over a coset of unipotent radical. Then we will also encounter the so-called constant term or leading term in the asymptotic expansion of a function of slow growth when you study its asymptotic behavior, restricting attention to a parabolic subgroup. We will say more details as and when we encounter them for the first time. Short space of rapidly decreasing functions start with Iwasawa decomposition Kan, the component of x in K, component of x in A, component of x in N. Define two special functions, psi and sigma. Psi is this integral. Rho here is half the trace for the joint action of this Lie algebra A on this Lie algebra N, which is the Lie algebra of the group N. Sigma x is the distance between the identity coset K and the coset xk in the Riemannian symmetric space. An element of the envelope.
By the way, Harish Chandra gave a colloquium talk in 1999 1969, and it was published in the journal also, and these next two screens are screenshot from that published paper by Chandra.
Algebra gives rise to a left invariant differential operator on the group and also the right invariant differential operator on the group. Take a finite product B of such differential operators. Take also a positive integer R and define these seminorms. Take only those functions for which all the seminorms are finite. That is the short space CG of the group G. The seminorms gives rise to a topology on the short space. We will later say that distributions on the group which are continuous in this topology are tempered distributions. Our notation for the short space will change later. The space of completely supported functions form a dense subspace of this short space. The short space is closed under right translations and left translations by elements of the group. It is closed under convolution. The short space function is called a cusp form if all these integrals FQ vanish for every proper parabolic subgroup. This integral Fpx for a short space function always exists for any parabolic subgroup. The space of short cusp forms is closed in CG. It is closed under left and right translations by group elements. We denote by C0G for the space of cusp forms. A short space function is square integrable. The square of psi multiplied by a suitable negative power of 1 plus sigma the square of psi multiplied by a suitable negative power of 1 plus sigma belongs to L1. A locally summable function on the group psi, which is at most equal to a polynomial in 1 plus sigma times psi, defines a tempered distribution. Take a C-infinity function f, apply these left and right differential operators coming from the enveloping algebra to the function f multiplied by this polynomial 1 plus sigma to the power m. Suppose that is square integrable. Suppose this happens for all left and right differential operation by elements of the enveloping algebra and all positive integers m for the fixed f. Then this function actually belongs to the short space. These L2 norms for various choices, they define a semi-norm and the topology on CG defined by these semi-norms is exactly the topology of CG. Instead of the earlier notation for short space, we will now switch over to this notation for the short space.
Sorry, why are there two notations?
Pardon?
Why are there two notations?
No, as I said, the earlier one is notation used by Harishchandra. His 1969 European law, when it was published, this was the notation there. But now we are using cat with different. No, I don't want to use that. I don't know how to do that in cat. This one is what is everyone using.
The consequence of the assertion of the theorem in this slide and the corollaries in the next slide is the following. The invariant diagonal distributions theta lambda constructed by Harishchandra are locally summable functions. The theta lambda are locally summable functions and they define a temper distribution. The same conclusion also holds for any other invariant eigendistribution theta having the same infinitesimal character as theta lambda and having similar growth properties. While defining the orbital integrals, there are these fudge factors which are independent of the function.
Somebody told me that in many places the fonts are very small. Are you able to see the fonts in the back? On the back? You're really slowly.
I ignored giving an explicit description of them, but I'm still going to continue that negligence. But in any case, there is this statement here that if you differentiate this orbital integral with respect to a certain differential operator here, that extends continuously to the whole Cartan subgroup. What you see here is an equation which involves orbital integral of a function considered on two Cartan subgroups L and L1. Ff,
This is, we saw this making a choice of two adjacent Cartan subgroup yesterday for some other context, as we either pointed out, one is a Cayley transform, the other. And but today again we use the same thing but for a different purpose. Okay, let me.
L may not have a smooth extension at B where B belongs to the intersection of the two Cartan subgroups. That is why you see a right and a left derivative here for f of x. I ignored giving an explicit description of them, but I'm still going to continue that negligence. But in any case, there is this statement here that if you differentiate this orbital integral with respect to a certain differential operator here, that extends continuously to the whole Cartan subgroup. What you see here is an equation which involves orbital integral of a function considered on two Cartan subgroups L and L1.
Well, what I wanted to say was that this orbital integral is defined on a set of regular elements on the Cartan subgroup, but it may not have a smooth extension to all of L. But at points where you cannot extend smooth, it happens that if you choose, the other Cartan subgroup can be chosen in such a way that that extension possible for that Cartan subgroup, and the left derivative minus the right derivative is related by this going between two Cartan subgroups. That is what Harishchandra says here.
FFL may not have a smooth extension at B where B belongs to the intersection of the two Cartan subgroups. That is why you see a right and a left derivative here for FFL. They may not be equal. On the other side of the equation, we see the orbital integral with respect to the other Cartan subgroup, FFL1. It is so chosen that it is smooth at the same point B. A Cartan subgroup has a decomposition into, there is a maximal compact and there is a vector part, and it is the product of the two. Here this Li is in the Lie algebra, that is the Lie algebra of the maximal compact, and Lr, that is the Lie algebra of the vector part. It is called a fundamental Cartan subalgebra if the Li has maximum possible dimension. All fundamental Cartan subalgebras are conjugate. A Cartan subalgebra is fundamental if and only if it has no real root. If L1 is not fundamental, there is another Cartan subalgebra L such that Lr is of codimension 1 in L1R and L1I is of codimension 1 in Li. So that is how we show the equation here is right here. That is how the two Cartan subalgebras are chosen. So if Z is the centralizer of L intersected L1 in G, the semi-simple part of Z is SL2. So let L1 and SL2 be the corresponding subgroups. The orbital integral FF, which is a smooth function on the regular set L prime, may not have a smooth extension over L. At such singular points, some right derivative may differ from the corresponding left derivative. But focusing attention on L intersected L1 intersected SL2, the singularity which may be present, preventing a smooth extension of FFL to that intersection, disappears when you attempt the same for F of L1. But focusing attention on L intersected L1 intersected SL2, the singularity which may be present, preventing a smooth extension of FFL to the intersection, disappears when you attempt the same for F of L1. Moreover, the right derivative of F of L minus the left derivative of F of L equals the derivative of F of L1 at a point of this intersection. That is an explanation of the things involved in that equation we saw at the start of the previous slide. In particular, this has an important consequence. So suppose the right side here, the derivative of f of L1 or even f of L1, suppose that itself is 0, which happens for, if you choose f to be a cusp form, you'll see it later. So if the right side is 0, then on the left side, the right derivative and the left derivative coincide, and therefore that orbital integral on L is actually has a smooth extension over that, over L intersected L1 intersected SL2. In fact, that has a consequence that the smooth extension is over all of L. This is a repetition of the orbital integral we have already seen. So the statement here is that the orbital integral gives rise to a continuous function from the short space of G to the short space on the open set of regular elements on the Cartan subgroup. You can see the orbital integral here again. If you take a root, it may either be a real root or an imaginary root, or it may be neither. It may take both real and imaginary values. Take the product of the co-roots corresponding to imaginary roots and differentiate the orbital integral that extends to a continuous function on all of them. Given a function f on the group G and given a parabolic subgroup Q, we define this function fq on the Levy part of the parabolic by integrating against cosets of the unipotent radical. This was the theme we used when defining a cusp form. A cusp form is one which is 0 every time you do this operation for a proper parabolic subgroup. The map f going to fq from the short space of G to the short space of M1 is continuous in the Short's topology, and it has nice properties with respect to differentiation by center of the enveloping algebra. If you have a Cartan subgroup which is non-compact, then you can look at the parabolic subgroups for which this C in the Levy part of the parabolic, the C is contained in the vector part of that Cartan subgroup. There is this nice relationship connecting the orbital integral on the subgroup to the map f going to fq for the parabolic subgroup. First, you average the given function f with respect to adjoint action by elements of the maximal compact. Then do this operation of going from f to fq using this average f bar, and you get a function on the Levy. For that function on the Levy, now you do the orbital integral with respect to that Levy. then you have this relation. So this has an important consequence for any cusp form. If you take a cusp form and then you average it with respect to adjoint action of K, that is again a cusp form. And now you take this operation of FQ, that is going to be 0 because it is a cusp form. So the right side is 0, so the left side is 0. So the conclusion is, if you take a cusp form, then the orbital integral for on any non-compact Cartan subgroup is 0. In this theorem, f is not a cusp form but only a short space function. For a compact semi-simple Lie group, there is this beautiful relation connecting the orbital integral and value of the function and identity element. This quantity, the differential operator, which is the product of co-roots, all the positive co-roots, that is alternating with respect to adjoint action by the Weil group on the Cartan subalgebra. The other quantity, that is invariant with respect to adjoint action by the Weil group. For a non-compact semi-simple Lie group, you start with a non-fundamental Cartan subgroup and you evaluate this quantity here. It vanishes because for a non-fundamental Cartan subalgebra, you have a real root and the reflection with respect to that, that is alternating on this first factor and it leaves the second factor invariant. So when you evaluate at 1, that gives 0. So for a non-compact semi-simple Lie group, this quantity here survives, if at all, only for a fundamental Cartan subgroup. An elaborate argument which eventually reduces to working with the Lie algebra of the real semi-simple Lie algebra, an elaborate argument. It eventually concludes that the left side is actually evaluating the function at that. By the way, I was hoping that this is an important formula in the derivation of the Hermann-Weyer's character formula for a compact Lie group, and probably Redlon will cover it. If it is not already answered, we will cover it now. Identity element. Recall that there is this general notion of convolution of two functions on a group. If you take what I want to show in this slide is what is the definition of the K Fourier component of those distributions theta lambda or any other invariant eigendistribution theta, what to the definition. A smooth function on the maximal compact and a short space function on the group G, then again you can do the convolution and the result is again a short space function. So here the notation for the short space goes back to Herschenberg notation. And moreover, f going to alpha star f is a continuous map in the short space of G. You can also define the convolution of a smooth function on K and a distribution on G. Alpha star theta on a test function phi is the following. Evaluate the distribution theta on alpha star phi, that is defined to be alpha star theta at phi. Take an irreducible finite dimensional representation of K, take the character chi delta of this irreducible representation delta, take the complex conjugate chi delta bar and multiply by the degree of the representation. If you do convolution of this alpha delta with an invariant eigendistribution theta on the group G, these are called the K Fourier components of theta. These K Fourier components are smooth functions on the group, and they're actually eigenfunctions for the action of the center of G, center of the enveloping algebra of G, with the same infinitesimal character as that of the distribution theta. You can always choose a finite linear combination of k Fourier coefficients to approximate the theta with a given finite number of semi-norms on the short space. This tells us at least that there is always a non-zero k Fourier component for a non-zero theta. We already noted in a previous slide the statement that the orbital integral of a cusp form is zero on a non-compact Cartan subgroup. Next, for the assertion about smooth extension of the orbital integral of a cusp form on a compact Cartan subgroup, the compact Cartan subgroup L has a cellular decomposition where the union of the open cells is the regular set L prime. Points belonging to cells of codimension 1 come under the consideration of this equation in an earlier slide, where we remarked that if the right hand side is 0, then on the left hand side the left derivative coincides with the right derivative. There is a general principle that if you can overcome abstraction to smooth extension at codimension,
That statement is a correction, and including the correction also here.
1 cells, then higher codimension cells is a
This is
walkover.
not something written here.
Sorry?
All this cellular,
No, not that. Well, let me.
The non-compact Cartan subgroup. Next, for the assertion about smooth extension of the orbital integral of a cusp form on a compact Cartan subgroup, the compact Cartan subgroup L has a cellular decomposition where the union of the open cells is the regular set L prime. Points belonging to cells of codimension 1 come under the consideration of this equation in an earlier slide, where we remarked that if the right hand side is 0, then on the left hand side the left derivative coincides with the right derivative. There is a general principle that if you can overcome abstraction to smooth extension at codimension 1 cells, then higher codimension cells is a walkover. That lost remark that if you can manage smooth extension over cells of codimension 1, then it's a walkover over cells of higher codimension. That was quite hasty and quite casual. You need to use the additional fact that all the derivatives of the orbital integral for a compact Cartan subgroup, they are bounded. Yes, they are bounded on the open set of regular elements of the compact Cartan. If you make use of this fact, then smooth extension over cells of higher codimension is easy if you know it for cells of codimension 1 and the open cell. Now let us take up theorem 2. If f is a z-finite function in the short space, then f is the cusp form. If f is z-finite, then fq will be z and c finite. Here MC is the Levy part of the parabolic subgroup Q, and z and c is the center of the enveloping algebra of the Levy MC. In particular, fq will be c finite. Moreover, f going to fq maps the short space of short space to short space. In a finite dimensional Euclidean space, there is no non-zero finite dimensional space of rapidly decreasing functions stable under all derivatives. So fq must vanish. That means f is a cusp form. Now let us look at theorem 3. So we want to prove that if there is a non-zero cusp form, then the group has a compact Cartan subgroup. And we also want to prove a converse. That is, if G has a compact Cartan subgroup, there is a non-zero cusp form. So let us start with the first assertion that we know that the space of cusp forms is non-zero. Take a non-zero cusp form F. If no Cartan subgroup is compact, then all the orbital integrals for all the Cartan subgroups is zero, because for a cusp form, the orbital integral of the non-compact Cartan subgroup is totally zero. Well, then the value of F at 1 can be read off from the derivatives of the orbital integral on a fundamental Cartan, so that there is going to be zero. And then if you replace F by its translates, F of x is going to be zero for all x. But that's a contradiction, because we started with a non-zero cusp form. So if there is a non-zero cusp form, then the fundamental Cartan subgroup is compact. Now we look at the converse. So
I'm saying theorem 6.1.2 and 6.1.3, but I'm using the this notation is from V.S. Varadara's notes 50 years ago for his Williams talk, which is published in the series of the workshop and but I think, okay, maybe I'll state the theorem, or I've already stated it in a different form.
G has a compact Cartan subgroup. That being the case, we can start with any one of Harishchandra's tempered invariant eigendistributions, theta lambda for every character lambda on the compact Cartan group, non-singular character lambda on the compact Cartan. Take convolution of this theta lambda by a smooth function on k, which is also k finite. That will be a linear combination of k Fourier components of that distribution. These Fourier components will actually be eigenfunctions for the action by the center with the same infinitesimal character as the theta lambda. Take a non-zero Fourier component. It is going to be an eigenfunction for the center. In particular, it is z finite. So if you know that this Fourier component is in the short space, you are done by theorem 2. But we do not quite know, we do not yet know that F belongs to this non-zero Fourier k component belongs to the short space. We only know that it satisfies some inequalities similar to the inequalities satisfied by the distribution theta lambda. This is where the concept of the constant form, that is, the constant term of in the asymptotic expansion of a tempered function. This is where that concept plays a crucial role. This is to quickly recall the definition of a tempered function on G. Fourier components of theta lambda are k finite, z finite tempered functions on G. Let U be a finite dimensional vector space on which the group K acts both on the left and on the right, and the two actions commute. This is the space of smooth tempered z finite functions on G with values on U, equivalent with respect to both the K actions. If F is such a function, its asymptotic behavior is essentially determined by its restriction to closure of A plus. Let sigma be the set of simple roots for GA. As A goes to infinity in closure of A plus, lambda log A may go to infinity for some simple roots lambda, while that may not happen for the rest. For a subset F of the set of simple roots sigma, define the usual standard parabolic subgroup PF equal to MF, AF, NF. For an element H in A plus, consider the values lambda H as lambda varies over the simple roots in the complement of F. among those take the smallest value denoted by beta fh. We take a smooth function f on g as before, that is with values in u, z finite, equating with respect to the left and right action by k. For each subset f of simple roots, we study the asymptotic behavior of f as a goes to infinity in closure of a plus in such a way that beta f log a goes to infinity. The fact that f and its derivatives are tempered, and the fact that an ideal of finite codimension in the center of the enveloping algebra Z of G annihilates f and its derivatives leads to the assertion in the theorem. What is this assertion? This assertion is about the unique existence of a constant term or a leading term, unique ff, that is the notation for the constant term. This is the leading term in the asymptotic expansion of the function restricted to a certain restrict f to m af plus, where af plus is exponential of the af plus in the Lie algebra. A leading term means that if you subtract the leading term from the function and you let the group element tend to infinity, the difference, that is the function minus the leading term, that difference goes to 0.
But you can ask, why can't I restrict the function itself? Why can't I say that that is the leading term? But that will not, if you restrict the function to the Levy itself, that will not belong to this space. So the assertion here is that there is a leading term belonging to this space.
The leading term is a function which has properties similar to the function f we started with, but on a smaller group, the Levy factor of the parabolic subgroup. The leading term takes values in the same vector space U, and it is equivalent with respect to the two actions of k intersected with the Levy group. As a function on the Levy group, it is smooth and it is tempered. There is a finite dimensional space of such tempered functions on this Levy group, which is stable when you differentiate with respect to the action of the center of the enveloping algebra of this Levy group. It is noteworthy that this constant term ff satisfies these differential equations. Mu f here is a homomorphism from the center z of ug to the center of um1f. There is also this transitivity property. You take the constant term at one step and go further down and take the constant term again. That is the same as taking the constant term all the way down at first step itself. We started this discussion on the constant term or leading term, prefacing it with the words, that is where the concept of the constant term plays a crucial role to draw your attention. We were in the middle of a discussion on some other theorem 2 and some other theorem 3. We completed an indication of the proof of this theorem 2. We also completed an indication of one side of this two-way implication. The other implication, that is, if the group has a compact Cartan subgroup, then there is a non-zero cusp form. For this, we took a non-zero K Fourier component f of one of Harishchandra's tempered invariant eigendistributions, theta lambda, for a non-singular character lambda on the compact Cartan subgroup. Theta lambda and its K Fourier components f are tempered and obey the same infinitesimal character for action by the center of the enveloping algebra. Just knowing that f is tempered is not enough for us. If we knew that f is actually in the short space, then we can immediately infer from this theorem 2 here that f is a cusp form. What we need here, namely that the K Fourier components of theta lambda belong to the short space, will follow from the assertion of this theorem. That is enough of going in circles, so let us remove this part of the screen from our view here and focus on this theorem 3. Theorem 2 here deals with 3 statements, and the assertion is that they are all equivalent. There is this finite dimensional vector space U on which k acts both on the left and the right, and the two actions commute. F is tempered, taking values in U, C finite, and K equivariant. The assertion of theorem 2 is that F is square integrable if and only if the constant term is 0 for all proper parabolic subgroups, and that if and only if F is a short space function. We are not concerned with the other statements of this theorem, except that this center of G has no vector part, which is a part of this assertion here. We are not going to take up the...
Well, for us, we took the K Fourier component of theta lambda. We do not know any of these 3 conditions. We do not know any of these 3 conditions. We only know that K Fourier component is a tempered function. It belongs to that space AG. So what's the difference?
Proof of this theorem 2, which takes up an entire section 6 in the article of Varadarajan in Proceedings of an AMS workshop in Williamstown 50 years ago. The proof of theorem 3 depends on theorem 2 and it uses...
By the way, somebody was saying yesterday that you said you try to download the journal PDF file. Were you very successful?
Yeah.
Oh, you did? Okay. Maybe you can after May 1, you can have everything there. The files for these lectures, the original DS for the PDF file. Not the one which I had posted in the IMSC website. That was a Xerox copy, but not the journal PDF file.
This lemma on the next screen. Theorem 3 uses... Theorem 3 in particular asserts that the K Fourier components F of theta lambda are all in the short space. The strategy is to show that all constant terms vanish and deduce theorem 3 using theorem 2. For each standard parabolic subgroup PF equal to MF, AF, NF, the constant term FF is a tempered ZM1F finite function on M1F equal to MF, AF. The lemma has 3 parts. 1. FF restricted to MF is tempered on MF and ZMF finite. Part 2. FF is constant on cosets of AF. Part 3. If the infinitesimal character of F is pi lambda, then FF is 0 unless S lambda restricted to AF is 0 for some element S of the ambient value of GC with respect to LC.
So, well, here I'm indicating, I'm reproducing, I'm getting confused. So that is the part which is important for us.
The fact that the constant term satisfies these differential equations and the fact that lambda is regular imply that for M in MF and A in AF, this function FF MA of the two variables M and A is a sum over the elements S belonging to the ambient value sigma FFSM times exponential S lambda log A. Group together terms for which S lambda restricted to AF are the same. All the S lambda restricted to AF are real linear forms. Group together the terms corresponding to S for which S lambda restricted to AF are the same. To get FFMA equals a certain sum, a finite sum, exponential lambda J log A times FFJM.
There is also the fact that
The consequence of the temperedness assumption implies that if lambda j is non-zero, then f of j has to be zero, because exponential of a non-zero linear form does not mix with a tempered function. So f of j survives, if at all, only for lambda j equal to 0. That gives the lemma. Suppose now that the conditions of theorem 3 are satisfied.
But, so, what is claimed here is that if the conditions of theorem 3 are satisfied, and suppose that this ff, there exists some f for which ff is not equal to 0, the constant term is not equal to 0, then choose one of smallest cardinalities. So below that, the constant term will be 0. But then you can take the constant term for the one with the minimum cardinality, and because of the there is this you do this take constant term one step and then take constant term again by going to a subset of f. That is the same thing as taking the constant term all at once in the beginning itself. Because of that transitivity, because of that, if you take the minimum cardinality where smallest set of f of smallest cardinality for which it is not equal to 0, then for any other lower cardinality it is going to be 0. Therefore, we will get the cusp form for that f, for that MF. So you get a cusp form there, and then you use that lemma to conclude that something restricted to that AF is 0. Okay, so you use that lemma to conclude this. So let us skip this part now.
We had said that the theta lambda will eventually turn out to be the distribution characters of discrete series representations. If pi is an irreducible unitary representation, we say that pi belongs to discrete series if the matrix coefficients of pi are square integrable. Let us recall that theorem 2 was a statement about three equivalent conditions, one of which was square integrability and the other one was that f is a short space function. In particular, the k-finite matrix coefficients of pi, discrete series representation, being square integrable and z-finite eigenfunction, f is therefore in the short space, hence f is a cusp formed by theorem 2 and 3. That is so for every matrix coefficient f of pi, which is k-finite and z-finite. But when you have a non-zero cusp form, we know that G should have a compact Cartan subgroup. Conversely, if G has a compact Cartan subgroup, you have a non-zero k-finite, z-finite cusp form f. In particular, it is square integrable. The L2 closure of the G translates of f would be the finite orthogonal sum, each summand being a discrete series representation. So G has a discrete series even only if there is a compact Cartan subgroup in G. This is a formula A here. This is a formula we have seen before for evaluating a tempered invariant eigendistribution on a cusp form f using orbital integrals. From Harishchandra's formula for the tempered invariant eigendistributions theta lambda on a compact Cartan subgroup, we know that when you multiply theta lambda by the value denominator delta, that is the basic alternating sum over the well group of K of non-singular characters psi lambda corresponding to lambda. You also have this formula for evaluating an invariant eigen distribution theta on a cusp form F. Phi here is the analytic function on B that extends the product of the y denominator with the restriction of theta to the regular elements of B. If you do this, taking theta equal to theta lambda, then it is immediate that theta lambda f is this right hand side. On the right hand side, you see a Fourier transform on B. Let us again look at this equation A. Apply Fourier transform on the compact torus B to this quantity in brackets. There are two quantities here. The first one is this differential operator. The second one is this FFL, which is a smooth function on all of B. B and L are the same. From elementary Fourier theory, we know that applying this differential operator to FFL and then taking Fourier transform is the same as first taking the Fourier transform of FFL and then multiplying by this polynomial. This polynomial vanishes at singular lambda. That is why the summation here involves only non-singular lambda. On the compact torus, evaluating a function at 1 is the same as taking the sum of all the coefficients in the Fourier expansion. That is in essence how you should understand this equation, by replacing the function f by its group translates. This is what Hermann Weyl did for compact Lie groups. That is also what Harishchandra achieved here. It was a monumental achievement, overcoming tremendous difficulties from non-elliptic regular elements and semi-regular elements. It cost him depression and health issues. Take theta lambda. How many other theta mu have the same infinitesimal character as theta lambda? Here you see coset representatives for this smaller Weyl group in the bigger ambient Weyl group. So there are this many distinct theta mu with the same infinitesimal character as theta lambda. If you restrict theta omega to the compact carton and multiply by the Weyl denominator of the compact carton, that is an analytic function which is alternating with respect to the action of the Weyl group of K. So it is a linear combination of basic alternating functions. These basic alternating functions are the ones given by Harishchandra's construction of theta si lambda, which you see on the right side. A temporary invariant eigen distribution is completely known if you know the restriction of that temporary invariant eigen distribution to a compact Cartan subgroup. So you have a formula for theta omega as a linear combination of the theta si lambda. I will go to the next slide here and expand it in the form of a certain matrix there. F would be orthogonal to all the phi omega. That would lead to a contradiction as the L2 span of F and its the theta omega have to be linear combinations of the theta lambda because of the infinitesimal character consideration alone. But it cannot span a smaller subspace because you can take something which is orthogonal to this span, if it is a small subspace. You can take something orthogonal to this span and take k-fluid component which will give some other discrete series which we not take into account. So G translates would have an irreducible component, that is a discrete series representation not to be found among any of the omega. It follows at this stage that if you fix an infinitesimal character chi equal to chi lambda, then the number of distinct theta si lambda with that infinitesimal character and the number of distinct discrete series representations with that infinitesimal character, both the numbers are the same. What we have been doing is to indicate a proof of the classification theorem of Harishchandra, that is, he classifies a discrete series by its distribution character, and conversely he says that the distribution character, the characters invariant eigen distributions theta lambda which he constructed are actually, if you choose the sign properly, they're actually the distribution characters of a suitably chosen discrete series representation omega. We are very close to completing the indication of the proof of this theorem. This is a matrix representation of the fact we saw that the character of a discrete class, the distribution character of a discrete class, theta omega, is a scalar combination, linear combination of the theta si lambda.
Okay, so this is an invertible matrix is what all that remark was about. These things cannot span a small subspace or the subspace span that is. Okay, so this is an invertible matrix, but Harishchandra shows that this matrix is actually integral, and actually this, the orthogonality relations for discrete series together with the fact that these are representatives for these cosets. So these are also have an orthogonality property. So this matrix is actually unitary, and then Harishchandra wants to show that this is actually integral. The way he shows that it's integral is by looking at something like the multiplicity of, so to say, multiplicity of k finite representations of k here in a discrete series, and these characters also you can formally invert from the denominator something, some part other than the well denominator of k, and if you invert that will also appear to be integral multiplicity. So that is what he uses to conclude that this matrix is an invertible, unitary, integral matrix. Therefore, it has to be a permutation matrix with plus or minus 1. So let's keep this now.
That completes the indication of the proof of the classification of Harishchandra of discrete series representations by their characters.
Well, you should be happy. So, I think too much part for standard.
And such a nice and large audience. I haven't spoken to such a large audience in a long time. It's still not on. Actually, local periodic, and I'm supposed to talk about something global. So this is you might find lots of mistakes, signs, constants, etc. in the view of. I'll try to give some things. Okay, so let's begin. So, what are some of the most basic versions of spectral decomposition that one sees? First is diagonalizing a linear operator which is diagonalizable. It's the same as saying that V has the vector space or inner product space V that has a direct sum decomposition into multidimensional spaces indexed by the multi-set of eigenvalues of T. Okay, counting with multiplicity. So, for each element of the multiset, you have the corresponding eigenvalue lambda of x, and so V is a direct sum of copies of C on each of which T acts by as a multiplication operator. The next case is, you have not just one operator, but you have multiple operators and they commute with each other. And you are again assuming that G acts diagonalizably. And then one can talk about a similar decomposition. Instead of looking at all the eigenvalues, you will be looking at all the eigencharacters. And the third case that I want to discuss is, mention is if a group G acts completely reducibly on V, you can talk about the same thing except that G is not abelian this time. So you can't simultaneously diagonalize. So the best you can do is take a similar direct sum over irreducible representations of G occurring in V. And in the abelian case by Schur's lemma, this reduces to the previous one. Okay. So this is the kind of what we mean by spectral decomposition. So let us look at some observations in the infinite dimensional case. So if you have an infinite dimensional Hilbert space, self-adjoint or normal operators may not be diagonalizable. We will see an example in the next slide. But we know that compact self-adjoint / normal is. And then we have the one infinite dimensional familiar case that we study is the theory of Fourier series, S1 acting on L2 of S1 by left or right regular multiplication. So you have these trigonometric functions z goes to z raised to n. They form a Hilbert space basis. That's why there is a hat of L2 of S1. So this here the convergence is in L2, and for better functions you can ask for better convergence. And again, you see L2 of S1 is being decomposed into a Hilbert space direct sum of irreducible representations of S1. And these are parameterized, these are just characters of S1 because S1 is abelian, compact. And then we have the example of the Peter-Weyl theorem, which was discussed in the Bhaskaracharya-Pratishtha lecture series recently. If you have a compact topological group, G acts on L2 of G by left or right regular representation, and we have this familiar decomposition of L2 of G into irreducible representations. Okay, or you could decompose the action of G cross G on L2 of G, which is better. Now let us look at some slightly more general versions. So in infinite dimensional case, I said that there are examples which are self-adjoint but not diagonalizable, and one of the most commonly cited examples is multiplication by the function f of x equals x on F2 of 0, 1. It's easy to check that this is not diagonalizable. So self-adjoint and normal does not automatically imply diagonalizable, but you can reinterpret the diagonalizability and get a criterion which is satisfied by self-adjoint operators, which is that to reinterpret the finite dimensional case, if you have a self-adjoint T from V to V in the finite dimensional case, we had written down this decomposition in the first page. Each Vx is a copy of C, and a direct sum of x many copies of C can be thought of as just L2 of x. Okay? So if you choose an orthonormal diagonalizing basis for T, what one is doing is, one is choosing a unitary isomorphism from V to L2 of x, and this isomorphism transports your original operator T into multiplication by the function lambda. Okay, that's the meaning of diagonalization. Okay? So one way you can generalize diagonalization is that you can try to get an isomorphism from V to an L2 space so that your linear operator T becomes a multiplication operator. Okay? And that is so if you look at the L2 of 0, 1 example that's over there, it is automatically a multiplication operator. So the point is that in that situation, if you interpret diagonalizability this way, you don't need to do anything. Whatever is given is tautologically diagonalizable. And then we have a theorem called spectral theorem for bounded self-adjoint operators. Bounded self-adjoint operators on Hilbert spaces are unitarily equivalent to multiplication operators on some L2 of x. Okay. And one can interpret this as saying that, if you think of this as L2 of x, that L2 of x is a direct sum of copies of C indexed by x. Here the point is that you should just think of it as a direct integral of such spaces, where each direct integral of copies of C, where each copy of C corresponds to an element of x. Okay, any questions? Okay, so so then we have the example of Fourier transform on R, on L2 of R. So So this is what it says for a dense set of F which is nice, namely if F is of Schwarz class, or if F is L1 intersection L2 and its Fourier transform is an L1 intersection L2. We know that F has this Fourier inversion formula, and this Fourier coefficient F hat of psi has this expression that is written over here. So earlier we saw Fourier series for L2 of S1, and just like Fourier series for L2 of S1, this expresses F as a combination of various nice functions e raised to I psi x. However, this time you are not expressing F as a sum of such functions, you are expressing F as a sort of integral of such functions. Whereas earlier, F was a direct sum of the Fourier coefficient times these functions. This time F is an integral of the Fourier coefficient F hat of psi times these functions. Okay, so interpretation, you can interpret it the following way: with the right regular action of R on L2 of R, namely that's a translation action of R. L2 of R is a direct integral of irreducible representations of R, where what is the representation characterized by psi? It is the one-dimensional representation. It's a copy of C on which R acts by this e raised to y goes to e raised to I sin y. Okay. So you are decomposing L2 of R into eigenspaces, but as a direct integral of eigenspaces for the action of R. So this is like you are diagonalizing the action of R on L2 of R, translation action, because the translation action of R here on V psi it manifests as multiplication by the scalar e raised to I psi y. So it's a form of diagonalization, and we are not going to make this notion of integration rigorous, but we'll kind of intuitively accept that that sort of thing exists. Yeah, so note that these functions y goes to e raised to I psi y are not in L2. So these are very relevant to the decomposition of L2, but these are very, very nice functions which are not in L2, and yet these are very relevant to the decomposition of L2. So similarly, we'll try to decompose some other L2 space in terms of certain kinds of functions called automorphic forms. So that's what we'll try to do. So thus, unlike for compact groups, the description of L2 of G for locally compact groups always involves not a direct sum but actually a direct integral. Okay, we will not get into the details of what this means or anything more, but I just want to state that there is an abstract Plancherel theorem which decomposes L2 of a locally compact group in terms of in the usual Peter-Weyl sense, where you replace sum by an integral. But this sort of result is highly existential. We have various concrete groups of interest like GLN over various fields or over arrays, and we want to decompose such spaces more concretely. Even if we may not be able to describe it entirely concretely, we might want to identify a part of the decomposition as a direct sum and a part in terms of a direct sum on something else, and then we would like to get as much information as possible on these measures and so on. Okay. So yeah, in a sense, to the extent that we know representations, we would like some handle on the measures. Okay. So this is spectral decomposition, and notice that instead of G cross G acting on L2 of G, there are various other decompositions one can consider. We can consider G acting by the right regular action on L2 of G mod gamma for a suitable subgroup gamma of G. Okay, so that also we might want to decompose. And here are three interesting examples in this sort of subject. You often see these examples. So the first of these examples is where something like GLN of R acts on L2 of GLN of R modulo ON of R, or GL2N of QP over SP2N of QP, or it could be GLN of QP over or of a function local function field over the maximal unipotent maximal unipotent subgroup. Let's say all the upper triangular unipotent matrices and so on. So that's one case of interest. These sorts of Plancherel formulas. A second case of interest that one has is where G is a reductive. Oh, sorry, I did not say what is G here, right? I should have said G is a reductive group over Q. Here? I see, yeah. So I should have said that F is R, and sorry, F is Q actually. F is Q. so that I can talk of what is congruence or arithmetic. Okay, so yeah. So for instance, this could be like GLN of R over GLN of Z, or SLN of R over SLN of Z. And the third case is you have a finite extension f of q, f over q. In other words, it's a number field, or it could be a global function field. I've written global twice. You can consider L2 of G of Adels over F modulo G of F, and G of AF acts on this by the right regular action, and you might want to decompose this. Okay. So 3 contains the part of 2 which pertains to congruent subgroups. Okay. So 2 also deals with the case of arithmetic subgroups gamma that we will not bother with. Langland's theorem also applies to those cases, but we will only think of worry about the congruence case, in which case it can be studied by the action of G over Adels acting on G of AF over G of F. Okay. So this is the case that we are going to focus on from lecture 2 onwards, and we will always assume F equals Q just for psychological comfort, so it's not really necessary. Okay, any questions?
Previous slide, don't you need to define the hard measure?
Where?
So what is
Here.
D part?
No, here if you choose a hard measure, you have a decomposition, and hard measure is essentially unique.
What is d pi?
D pi, of course, that's, yeah, so the formal statement of the theorem will say that there exists a measure which is unique in a suitable sense. You know, all these things have to be made precise, etc., etc. Okay.
In your example, there is finite measure or?
Sorry?
In your example, there is a finite measure or?
No, these measures will be infinite in general. But you know, this is not this is something that I wrote down just for motivation. I mean, you know, it's an informal statement because this is we are going to deal with very, very concrete groups from now on. Okay, so and so today I'll only discuss upper half plane modular SL2Z. Okay, so so this is all the preliminaries before that. Okay, so I should also mention about unbounded operators. So d by d theta can make sense on smooth functions in L2 of S1. Okay, it doesn't make sense on all of L2 of S1, and yet you can talk of diagonalizing d by d theta on L2 of S1. Namely, it has a basis consisting of the trigonometric polynomials, and each basis is an eigenvector for d by d theta with eigenvalue 2 pi in. Okay, so in other words, you have a diagonalizing basis on which d by d theta is defined, so you can think of that as diagonalization nevertheless. Okay, but this also tells you that d by d theta cannot be extended continuously to L2 of S1, because if there existed such an extension, its norm would be greater than 2 pi in for all n, which would be infinity, a contradiction. Okay, so there is a theory of unbounded self-adjoint operators in a precise sense, which will need to take some care about domains, etc. But we are not going to kind of worry too much about those details. There are spectral theorems to diagonalize such operators. Okay, we'll again only intuitively relate to this. And similarly, recall that L2 of R, we wrote it as an integral of representations V psi, where each V psi can be thought of as spanned by x goes to e raised to I psi x. And notice that these guys are eigenvectors for d by dx with eigenvalue I psi. Okay, so it's all again like d by dx on L2 of R is being diagonalized, because whatever you are writing L2 of x as a direct integral of, those individual on those individual functions d by dx makes sense with these eigenvalues. Okay, so you are diagonalizing d by dx on L2 of R. So why do these two things look exactly like the Fourier transform or Fourier series that we saw earlier? The reason is that d by d theta spans the Lie algebra of S1 and d by dx spans the Lie algebra of R. These differential operators are obtained in exactly the way that we have seen so far by differentiating the relevant right regular representation. Okay, because S1 acts on L2 of S1, its Lie algebra acts on the smooth vectors of L2 of S1, and the Lie algebra is just the span of d by d theta. And similarly, the Lie algebra of R is spanned by d by dx that acts on smooth vectors in L2 of R. Okay, so that's why the spectral decomposition of d by d theta slash d by dx coincides with that of these groups. Okay, so often going to differential operators is actually a part of can possibly simplify study of spectral decompositions. Anyway, so this is special. So this is what I had written over there. Even the universal enveloping algebra acts on smooth vectors. Okay, so now let us finally move to the situation of today's talk. Okay, so H is the upper half plane and gamma is SL2 of Z, and SL2 of R acts on H by Mobius transformations. Okay, it in fact acts on the whole of P1 of C, the Riemann sphere, and this is the restriction of the action of G onto that.
Can you go back to the last slide and explain the special, like what is the general scheme?
Explain what?
The last little bit.
This one?
Yes, last section. Yeah, last.
See, the Lie algebra acts on the space of smooth vectors, right?
Yeah.
So you have a map from Lie algebra into the endomorphisms of the smooth vectors and by the universal property of the universal. Yeah, sorry.
So about this third point, so in this L2R, this functions x goes to e power I psi x.
Yeah.
These functions are not L2, right?
Yeah, that's what I mentioned in a few slides ago.
So this v psi doesn't appear as a sub-representation inside L2R.
Yeah, it does not appear as a sub-representation of L2 of R, and therefore it is. Maybe I shouldn't have said that. This is a special case of that, but but then the thing is, d by dx does act on smooth vectors in L2 of R, and then you can talk about spectral decomposition of that, and these B-sides are still relevant to that. Yeah, so you should interpret that in that weak sense. Yeah. No. Okay. So SL2 of R is going to be our G today. It acts on upper half plane by these Mobius transformations, and the stabilizer of I is SO2 of R, which we are going to denote by K today. This action is transitive, so this realizes upper half plane as a symmetric space G mod K, which is SL2 mod SO2. Okay, and because G and K are unimodular, the quotient has a unique G invariant unique G invariant measure up to scaling. And in the case of H, that is very explicit. It is dx dy divided by y square, and it also has other structures. Okay, so this is the case that we are going to discuss today. Okay, gamma acts on H in a very nice way, properly discontinuous, etc., etc. So for that reason, this quotient gets a measure from H. Okay, H to H mod gamma is locally a homeomorphism, so you can transfer the measures consistently. Okay, and one can show that this is of finite volume but not compact, and actually that is very easy because the action of gamma on H has a fundamental domain that has this shape, and you can so this is between minus half and half. Okay, so on this entire region you can check that let's say from here onwards dx dy by dy square integrates to something finite. Okay, so it is not compact, but the obstacle to the only place where it gets non-compact is basically the infinity. Okay, so it is non-compact. Okay, so let me repeat. This region is a fundamental domain for the action of gamma on H. This is not compact, but the thing is, if you add an infinity over here, it's going to become compact, and you can directly check that dx dy by dy square actually gives you a finite measure of that entire space. Okay? So it has finite volume. Okay, so this is the compactification that I wrote. So that infinity can be thought of as a point of the Riemann sphere. Therefore, gamma acts on H union infinity. You can talk of the quotient. And for this gamma, infinity is what is called the unique cusp. So whatever we discussed today can essentially be done for more general gamma, but there will be more complexities. There will be multiple cusps. Sometimes you will have to deal with interactions between cusps, but I will only deal with SL2 of Z acting on upper half plane. Okay. So the way to handle cases where there are more cusps is that you can use a matrix to transport that cusp to infinity, so to speak. SL2 of R acts transitively on P1 of R. So and then whatever we do with infinity, you can do with other cusps. Okay. So now we want to get some sort of spectral decomposition on L2 of H mod gamma, but for what right action? What is it that has a right action on L2 of H mod gamma? Okay, so H mod gamma is G mod K mod gamma, and because we have put a K over here, you cannot make G act on it. Okay, so when you quotient by K on the right, this L2 is the K fixed elements of L2 of G mod gamma. Okay. So if you right translate by G, that's going to destroy K fixedness. Okay, so G doesn't act here. So the first thing one might think of to act on that is normalizer of k over k. That is useless because there is nothing more. Second thing you can think of acting is Cc infinity of k mod g mod k, which we saw in Professor Narayana's lecture today. It's a good thing to do, but this is not what we will do today. Third thing you can make use to act on L2 of h mod gamma is the action of the Laplacian on which is the Laplacian on h mod gamma is y square times dou square by dou x square plus dou square by dou y square. Namely, h mod gamma has a Riemannian manifold structure. Any Riemannian manifold has a natural Laplacian, and this turns out to be that. Okay. So the point is, the action of the Laplacian commutes with the action of SL2 of R on H. Therefore, it is a well-defined operator on H mod gamma. Okay. So this differential operator acts on L2 of H mod gamma, and that's what we want to study. Okay. Now, how is it related to the action of G itself on G mod gamma? So here you can interpret it like this: G itself does not act on L2 of G mod K mod gamma. Therefore, G and universal enveloping algebra, the Lie algebra and the universal enveloping algebra do not act either. But the point is, the center of the universal enveloping algebra nevertheless acts, because by definition center commutes with everything. So you can commute it past k, so it stabilizes functions which are k fixed. Okay, and I think Professor Narayanan mentioned that this center is generated by a single element omega, the Casimir. Okay, so to study the action of the center of the universal enveloping algebra, it's enough to study the action of the Casimir operator on L2 of G mod K mod gamma, and one can check that the action of the Casimir on smooth functions is the same as that of the Laplacian. Okay. So the point is, the center of the universal enveloping algebra, it doesn't look like a large enough thing. It certainly is the center of something, right? So it cannot tell you everything about the action of universal enveloping algebra. But the point is, it is still large, still pretty large, and therefore this still captures a lot. Okay. So I think, yeah. So for instance, you look at SL2 of R. You look at a discrete series representation. There are only three representations that it shares infinitesimal character with. One of them is itself. Another one is a brother discrete series representation or sibling discrete series representation, and the third one is a finite division representation. Okay. So center of universal enveloping algebra can cut things down a lot. So if you want to study the action of G on L2 of G mod gamma in the special case of L2 of G mod K mod gamma, studying the Laplacian still tells you a lot. Okay, so that's what I want to discuss today. Any questions?
Would you repeat the last point?
Yeah, so the Laplacian is basically the action of the Casimir, and therefore it generates basically the whole of the center of the universal enveloping algebra, which captures a substantial portion of the representation theory of G. Okay, so that is, if you know how the universal enveloping algebra acts on a given irreducible representation, you cannot recover the irreducible representation. But in many cases, you can cut down irreducible representations a lot. Okay, so in fact, Professor Parthasarathy's lectures also, he was using characters of the universal enveloping algebra to prevent various principal series representations from coming and spoiling the uniqueness. So this is why center of universal enveloping algebra is important. It's quite large. Okay, any other question? Yeah.
Is it easier to study L2 G mod K mod gamma than L2 G mod gamma? Why is it?
Well, in this case, upper half-line mod gamma is some concrete thing where you can lay your hands on. So,
Okay.
I mean, yeah, but still, yeah, I don't know. There may be difference of opinion. I think, and many people use this as an example to illustrate general, like even Lapid and Bernstein, when they want to explain meromorphic condition of Eisenstein series, they first explain it in this case rather than spin. So, okay, so let me now discuss what are mass forms and automorphic forms. So we will be interested in two kinds of functions on H mod gamma. One is L2 of H mod gamma itself. That's what we want to decompose for the action of the Laplacian. Second thing is that the decomposition of L2 for this decomposition, there will be other nice functions which are not in L2, just like for the Fourier transform on R, which are nevertheless relevant for the spectral decomposition. Okay, and those are what we are going to call as mass forms or automorphic forms. I'll use these two terminologies interchangeably. Okay. So here is the definition of a mass or automorphic form on H mod gamma. These are functions from H mod gamma to C that are, first of all, they have to be smooth, so not arbitrary L2 function. Secondly, we want spectral decomposition of delta, right? We want a diagonalizing basis with respect to delta, because that is what spectral decomposition means, which means you want to consider eigenfunction for delta. Those which satisfy delta f equals lambda f for some lambda element of C. Okay. So in Professor Ravi Raghunathan's lectures, this condition will be kind of replaced by, it generates a finite subspace under the action of universal Euclidean algebra. I mean, assuming okay, but here we will only be considering eigenfunctions as automorphic forms. Then at the unique cusp, you see, H mod gamma is not compact, but the non-compactness is entirely captured by infinity. So to study how a function on H mod gamma grows, it's enough to study its behavior as y goes to infinity. Okay, y means the y coordinate in the complex plane. So the condition is that it should be moderate growth at infinity. That is, as y goes to infinity, the function should grow lesser than some fixed power of y. Okay, so there will be some n depending on f, so that the growth of f will be bounded by that. Okay, so these are the three conditions that are there. Okay, so many aspects of analysis of asymptotics, etc., seem to require this condition quite a bit, and that seems to be why this condition is thrown into the definition. So this is just for y. If you wanted more general gamma than SL2 of z, then there will be multiple cusps, and you will need these sorts of conditions adapted to every cusp. Okay, but I will not keep making these sorts of disclaimers henceforth. Okay, so even before stating the spectral decomposition, let me say what it is going to look like. Okay, we want to decompose L2 of H mod gamma into a discrete part and a continuous part, so to speak. Okay, and we'll see later what these are. Okay, this is just going to be how the theorem is going to look like. And then the discrete part itself, we are going to split into a so-called cuspidal part and a residual part. Okay, again I will define these much later. Okay, and for f element of L2 of H mod gamma, you are going to have some sort of an expansion like this. I am going to describe what this expansion is going to be. Okay, so f can be written as, you see, these UJs that I have written here are going to be some orthonormal collection of elements of L2 of H mod gamma. These are going to be what are called the cusp forms, and these VJs are some other orthonormal collection of elements of L2 of H mod gamma, and these are what are known as the Eisenstein series. Okay, so you are projecting from F onto the UJ component and multiplying by UJ. That's how you project from some Hilbert space to the span of a single vector, right? So you are projecting from F onto the UJ component and multiplying with UJ. Similarly with VJ, and this is a continuous version of that. Okay, so here these are all mass forms, and in particular they are eigenfunctions for delta. In other words, by doing this, you are diagonalizing the action of delta on L2 of H mod gamma. Okay? Okay, so compare with the Fourier inversions on S1 and R. So this term, this is how Fourier inversion on S1 looks like, and that's how the first two of these two terms are. So that they account for the discrete part, and the second term looks like Fourier inversion on S1, and that looks like the continuous part. Any questions?
So is it true that the Eisenstein series will be a mass form?
Sorry?
This EZ is the Eisenstein series. This will be a mass form.
Is it going to be what?
Mass form?
Yeah, they will be mass forms. But yeah, I won't give all the details of the proof, I'll just indicate some of that. Okay. Yeah, so the point is we want to expand this in terms of a diagonalizing basis, right? So, okay, any other question? What I mean is E of dot comma S are all mass forms. Okay, Z is a variable here. Okay, so the variable in which it is a mass form is Z and not C, not S.
So where S is varying from?
So here, here in the integral S is varying over IR, but it's going to vary over C. But this is just a statement of what is going to come. Okay, so I am only going to define these terms later. Okay, so how does one construct mass forms? Okay, so these have to satisfy two conditions. They should be, see, whenever I say function on H modulo something, I'll be thinking of a function on H which is invariant under the action of that thing. Okay, so in other words, you want a gamma invariant function on H, and moreover, it should also be eigenfunction for the Laplacian. Okay, so how would you construct? Okay, so try to average with respect to gamma. Okay, so let us first look at the Iwasawa decomposition. It says that if n is the upper triangular unipotent matrices and A consists of the diagonal positive matrices and K is SO2 of R, then this multiplication is a diffeomorphism. Okay, it's not a group homomorphism or anything, but it's a diffeomorphism. Okay, so how does that manifest for H, which is G mod K? If you take an element 1x01 of n, root y 00 root y inverse of A and any element of SO2 of R and act it on the element I of upper half plane, the n will act as just the x and root y will just become the y coordinate. Okay, so acting by this element is basically multiplying by y, and acting by 1x01 is just translating by x. Okay, so this is what the Iwasawa decomposition says, and clearly n times A acts simply transitively on the upper half plane. Using this, you can prove the Iwasawa decomposition in this case. Okay, but let's not get into that. So the point is, H mod n is a much simpler space because n means translation with respect to the x coordinate. So H mod n involves just the y coordinate. It's just looking at the y coordinate, and that is just open interval 0 infinity. Okay. So since this is a much simpler space, the idea is to choose a function on H mod n, and then that's only invariant under n. It's not invariant under gamma. Okay, so n contains part of gamma, it doesn't contain all of gamma. So you basically sum it over gamma modulo gamma intersection n, so to speak. Okay? So that's how you construct functions which are invariant under gamma. So one defines gamma infinity to be the stabilizer of infinity in gamma, and you can check that there is plus or minus 1 times n into n intersection gamma. So if you take something which is already invariant under n intersection gamma acts trivially on it, and plus or minus 1 anyway acts trivially on the upper half plane, and therefore gamma infinity acts trivially on any function on H mod n. Okay, so you don't need to sum over all of gamma translates, you only need to sum over gamma modulo gamma infinity. Okay, so you take a function on H mod n that is automatically invariant under gamma infinity but not under gamma, so you force gamma invariance by summing over gamma mod gamma infinity translates. Okay, and this preserves delta eigenfunctions because delta commutes with the action of SL2 of R. Namely, if your original phi, you think of phi as a function on H, if it was delta eigen, then this new function is also going to be delta eigen. Okay? Yeah, so I haven't talked anything about the convergence, I'm going to discuss that. So one way to think of what I just described is as follows. You can think of H mod gamma infinity and H mod n. Okay? So gamma infinity is plus or minus 1 times gamma intersection n. So n is like a copy of R, right? 1x01, and gamma infinity is basically like the z inside R, that R. Okay? So this projection has fibers that look like R mod z. Okay, so this projection has compact fibers, and I mean, of course, this projection is nothing of the sort. Okay, so y, which is R mod z cross 0 infinity, because you see, when you act by gamma infinity, basically you are translating by integers. So, you see, z itself was 0 infinity, this we saw in the previous slide, and y is just R mod z cross 0 infinity, that's why this projection has compact fibers. So the above construction that I mentioned, the Eisenstein construction, is simply given a function here, you are pulling back under this map which has compact fibers, and then you are pushing forward along this map. Okay? So that's how you get Eisenstein construction. Okay? So there are two variants of this construction that we will look at. One where you start with a function on H mod n which is in CC infinity. Okay? This has the advantage of being CC infinity, but it's not going to be delta eigen or anything of that sort, but it will be CC infinity which is so CC infinity of 0 infinity, and then you define E of Z phi in this fashion. Okay, so given such a phi, so you get an element E of dot comma phi, and it's very easy to check that it is in CC infinity of H mod gamma. Pullback could have destroyed CC infinity in S, but this is actually a compact. This has compact fibers, so it doesn't destroy compact support. Whereas this pushing forward never destroys compact support. Okay, modular appropriate thing. So this is in CC infinity of H mod gamma, but it's not a mass form. And this sum can be checked to be locally finite, again using all that we have discussed about this map. So that's the first thing that you would do. Second thing, you don't start with a CC infinity function, but you start with something that is delta eigen, nevertheless not CC infinity. Okay? So what is Laplacian eigen on 0 infinity? Something which is eigen for d by dy or d square by dy square, etc. Right? Times y square in this case, right? So on H mod n, Laplacian acts as just y square times d square by dy square. So any power of y is delta eigen. That's why you consider functions which take x plus I by 2 y raised to s plus half. Okay? In this case, let us ignore convergence for now, it's a non-trivial issue. Okay? So the definition of E of z comma phi in this case is going to be summation gamma in gamma mod gamma infinity. Y means what? X plus I by goes to y means just the imaginary part. But you have to apply it not to z but to gamma z because you are averaging over, summing over gamma mod gamma infinity, and then you are raising by s plus half. Okay? And you can check that this equals whatever I have written on the right hand side here. Okay? So this is a definition of the usual Eisenstein series. The earlier way was pseudo Eisenstein series. Okay? So as you can see over here, in the second sum only m and n are varying. So once real part of s becomes larger, the convergence of this becomes better. Okay? So at least for real part of s large enough, we can hope that this guy converges. Okay? So these are the two kinds of Eisenstein series that we will need to deal with. Any questions?
Is there a 2s in the denominator?
Yes, I think so. Yeah. Thank you. Yeah. Sorry, my bad. Yeah. It has to be 2s plus 1. Sorry. Thank you. So usually, when you read the expositions on H mod gamma, people often do not put the half. But from the point of view of automorphic representation theory, when we deal with G of R mod gamma, that half is actually much more convenient and it gives us pleasanter functional equations and such. So that's why I have added this half. So it's a slightly different normalization of the Eisenstein series that one might often see. This is what is called the mass Eisenstein series, This is different from the Eisenstein series that you see in the classical holomorphic modular forms. Okay? So here we are looking at functions on H mod gamma. These functions are not holomorphic at all because if they were classical holomorphic modular forms, they would extend to H mod gamma, H union infinity mod gamma, and by compactness, and holomorphy they would have to be constant. So none of this is holomorphic. So this is a different kind of thing started by Mass in 1949 called mass forms, and this is the mass Eisenstein series, not the usual holomorphic Eisenstein series. Yeah, I made the same mistake. In the sense, Okay, so one can check that this converges for real part s greater than half. Okay, and so it's a function of both z and s. Oh, this is a typo. Sorry, I should have written z here. Okay, not s. Maybe I might have made this. Yeah, here also it should have been. Yeah, so this phi was phi s. That's why I wrote here. But it was better to write z e of z comma s. Okay, because phi s is completely determined by s. Okay, so e of z comma s is holomorphic in S and smooth in Z. Okay, one can check that. I'm not proving any of those results. And then it's easy to compute that y raised to s plus half is Laplacian eigen with eigenvalue s square minus 1 by 4 because that is what s plus half into s plus half minus 1 is. Okay, and since summing over gamma preserves delta eigenness, the Eisenstein series is also delta eigen with the same eigenvalue s square minus 1 by 4. Okay? And one has to make this estimate. You can check that this Eisenstein series is of moderate growth for real part of s greater than half. and therefore it satisfies all the conditions for it to be a mass form. Okay? So namely, once you fix S as a function of Z on the upper half plane, modulo gamma, it's a mass form. Okay? And here is a fact that we will comment on later. The definition, so though we defined E of Z as so far only for real part of S greater than half, by metamorphic continuation you can extend the definition to S element of C, implies outside a discrete set of S, you get a mass form with Laplacian eigenvalue S square minus 1 by 4. Okay, by analytic continuation. Okay, and it's a fact that although mass forms are never holomorphic, they are still real analytic, and we only impose a condition of moderate growth on it, but we also have an extra property called uniform moderate growth, which means that how much ever you differentiate it or act, all the derivatives of mass forms also have moderate growth.
Sandeep, the powers of modulus mz plus n should be 2s plus 1.
Yeah. So it was corrected in the previous slide. Yeah. So sorry.
People at the back in order for it.
Oh, okay. Yeah, maybe I should speak louder or something. Okay, no response.
It shows that people are still listening.
Or they couldn't hear the question.
Sandeep, I had a question.
Yeah.
So you said that the action of Laplacian is the same as the action of the Casimir operator.
Yeah.
But the Casimir operator would not be elliptic, whereas the Laplacian would be elliptic.
Okay, so but the Casimir is probably not elliptic on functions spaces involving G. This is only on H, right?
Oh.
Yeah. So how do we study the behavior of E of Zs? So asymptotics of mass forms involve studying their asymptotic behavior as y goes to infinity, right? So given a mass form, how can you study this asymptotic behavior? Okay? So that involves the theory of what is called constant term. In the setting of local representation theory for real groups, we saw that in the previous lecture. Okay, but here we'll see the setting of H mod gamma. Okay, so remember that you had this H mod gamma infinity mapping to H mod gamma, and that in turn mapped to H mod n. Okay, so if F is a mass form on gamma H mod gamma, we define its constant term F0, which is going to be a function on H mod n, which is 0 infinity, as follows. Okay, so F0 of x plus I by, it will only depend on y because it's going to be a function on H mod n. And what do? You integrate 0 to 1 f of x plus I by dx, though I should have written f of t plus I by dt because I already have an x here. Okay, but the point is that it is already invariant under translation by z, which is in gamma infinity. So you only need to integrate this over R mod z. Okay. So that's the definition of the constant term. So another way to put it is that f0 of z is just integral n mod n gamma infinity intersection n f of n times z dn. Okay. And it's a fact, I am of course not going to prove it, that f of x plus I by minus f0 of x plus I by decreases faster than any y raised to minus n as y goes to infinity. Okay. So f itself did not increase, increase slower than some y raised to n. Okay, there exists some, say f may be growing slower than, let's say, y raised to 1000 or something. Okay, but if you subtract f0 from it, it's going to be decrease faster than y raised to minus 1000, for instance. Okay, so which means that any automorphic form f and its constant term f0 have the same asymptotic as y goes to infinity. Okay, I mean that's informally how you can read it. So again, I think this property needs to use the uniform moderate growth. Otherwise, this is not going to be true. Okay. For more general gamma, one has to define a constant term for each cusp and study the asymptotic near that cusp. But I am not going to go into it. So here is a fact: for the Eisenstein series E of dot comma s, the constant term is of the form y raised to s plus half plus c of s y raised to minus s plus half. Okay. So if you look at this expression, no matter what s you choose, this fellow is not going to lie in L2 of H mod gamma because one of these is at least is going to be greater than y. s plus y raised to s plus half or y raised to s minus half, and integral y times dx dy by d square is not going to converge. Okay? But if s is imaginary, though it is not going to be in L2, you can see that it's kind of close to L2 because the integral is like integral y times dx dy by y square. If it was any smaller power, y raised to 1 minus epsilon, it would have converged. Okay? So it's on the imaginary line, this is kind of getting close to L2 but not quite being L2. Okay? The imaginary line is going to be important for us. Okay? So recall that f minus f0, the constant term, decreases faster than every y raised to minus n. So you define f to be a mass cusp form if the constant term is identically 0. Okay? And the space of mass cusp form by A cusp of h mod gamma. Earlier I had written, though I forgot to say it aloud, that A of h mod gamma was the space of all mass forms. Okay? So in other words, because f0 is 0, any cusp form decreases faster than y raised to minus n for all n. So this guy is contained in L2 of h mod gamma. Okay? So though not all automorphic forms are contained in L2, the cusp forms are still contained in L2. Okay? This decreases faster than every y raised to minus n, and h mod gamma has finite volume, so the L2ness follows. Okay? For cusp forms. Okay, so L2 cusp of h mod gamma is a closure of A cusp of h mod gamma, and you can intrinsically define it similarly, except that you have to add an almost all. Okay, so this defines one of the three terms in the decomposition of L2 that I said we will discuss. The first term was L2 cusp. The others were L2 res and L2 cont. So this is L2 cusp we have defined, and we are saying that delta can be diagonalized on L2 cusp of h mod gamma. So what does it mean to say that delta can be diagonalized? It means that this L2 cusp has an orthonormal basis uj consisting of eigenfunction for delta, namely mass forms. Sorry, I should have written that is. Okay, so what that means is that for all f elements of L2 cusp of h mod gamma, f can be expanded like this in terms of these uj's. So these are the uj's that I stated in the theorem that I mentioned earlier. Unlike e raised to in x etc., we don't have concrete expressions for these. Concretely, we don't know how to construct mass forms, but I mean, we have some techniques, but we can't describe their set or anything. But we know that there is some orthonormal basis consisting of mass forms. Okay. So in other words, you have this expansion, and moreover, the eigenspaces have finite dimension. Okay. And if f is nice enough, then this convergence, which was a priori in L2, can be said to be absolute plus uniform on compacts. Okay. So the point is, this theorem is not entirely, not at all trivial. So you see, when we study Peter-Weil theorem for compact groups, one important result is that if you take a CC function on G, the right regular action by it on L2 is a compact operator, and that is used to deduce finiteness of multiplicities. Okay? So if G is locally compact but G mod gamma is compact, once again, the right regular action by any CC of G is going to be a compact operator, and you can deduce finiteness of multiplicity and discreteness of decomposition from that. Okay? For general G mod gamma, that's not going to be true. It's only going to be compact if you restrict the space of cusp forms. So it's a very standard theorem that if you have G of R mod gamma, L2 cusp of G of R mod gamma is going to have a discrete decomposition as a direct sum of automorphic representations with finite multiplicities. Okay? Here the problem is that you can't talk of delta being compact because this is anyway unbounded. So you have to use resolvents to construct appropriate compact operators which commute with delta, namely Hilbert operators which are Hilbert fit and therefore compact, which commute with delta, and then kind of somehow achieve this. Okay? So, but let me not say anything more on that. So now let us study the orthogonal complement of L2 cusp of h mod gamma. Okay? So from CC infinity of h mod n, we can go to CC infinity of h mod gamma, which was a pseudo-Eisenstein series construction. And then we also define this constant term, which can be defined in this generality. And here is a very easy lemma. If phi is in CC infinity of h mod n and f is in C infinity of h mod gamma, applying the Eisenstein construction and then pairing with f is the same as applying the constant term on the second variable and pairing with the given function. Okay? So what does this look like? You see, I said that Eisenstein construction can be looked at as pulling back with respect to a certain map and pushing forward with respect to a second map. Constant term is exactly the opposite, and to push forward a function and pair it with a second function is the same as pulling back the second function and pushing forward with the first. Okay? So that's why this equation follows. It's kind of a formal thing. Okay, but what that follows is that if you take f to be a cusp form, then f0 is going to vanish. Therefore, E of dot comma phi is going to be orthogonal to f. Okay, so from this one can show that the span of pseudo Eisenstein series is precisely the orthogonal complement of the space of cusp forms. Okay, so once you have decomposed delta on L2 cusp, what remains is to decompose L2 delta on this remaining space, which is a span of pseudo Eisenstein series. Okay, so for that we need to discuss Melton transforms. Okay, so if you have a function in 0 infinity, you can define what is called phi in 0 infinity. You can define what is called its Melton transform. Integral 0 to infinity phi of r raised to minus s dr by r, and then the inverse Melton transform, which is what is so that Melton transform is what I have denoted by m phi, and this process is what is called the inverse Melton transform, and you can recover phi from it. Okay, so how do you see this? This is actually very easy. You just look at Fourier inversion. That's that's an inverse. Fourier inversion is a formula for functions on R, but this guy is just the group R greater than 0, and these two groups are isomorphic. So if you just translate Fourier inversion by this isomorphism, you are going to land with this. Otherwise, you can also think of as this is R greater than 0, and IR is indeed the Pontryagin dual of R greater than 0. Okay, so this is just Pontryagin duality, but anyway you have this thing. Therefore, how do you do the spectral decomposition of pseudo Eisenstein series? We might be tempted to do the following. We start with summation phi of gamma z, and then each phi of gamma z you write it in this fashion. Okay, integral m phi of s times imaginary part of gamma z to the s, and then you take this sum into the integral. Okay, this is what one might be tempted to do. Okay, because m phi of s does not see the gamma that you are operating over here. So you might be able to write the pseudo Eisenstein series in terms of the usual Eisenstein series like this. This is what one might be tempted to do. But the problem is that this does not have convergence on S element of IR, so the above switch of integral and sum is not valid. And for a good reason, as the theorem stated earlier said, the orthogonal complement of cusp forms cannot be entirely captured by Eisenstein series. There is also some of what is called residual spectrum. Okay, so what does one do? What one does is that this sort of a switch of integral and sum would have been valid if instead of IR, you were integrating on a line where the real part of S is large enough. Okay, so the point is that although in this expression, I integrated the Melton transform only on IR, using some estimates you can show that you could as well integrate over real part of S equals any sigma. Okay, and I just translated by half because but that anyway preserves lines of this form. So you cannot get exactly this expression, but you can get a similar expression with real part of S equals sigma. Okay, so anyway, if you did not follow all the details, that is fine. The upshot is that we can write the Eisenstein pseudo Eisenstein series in terms of the Eisenstein series. Okay, so that's just the take home message from here. You start with a pseudo Eisenstein series. You can write it as inverse Melton transform of the element phi that you started with, integrated against the Eisenstein series. Unfortunately, not on real part of S equals 0, but on real part of S equals any positive sigma. Okay, you can just take this on faith even if the argument was. Okay, but then we want to move to real part of S equals 0. So we want to shift the contour to IR. Okay, so you have you want to shift the contour from real part of S equals 1 to real part of S equals 0. But then in between there are going to be residues. Okay, and what are those residues going to be? The point is that so the residues will come because this guy has poles. Okay, this fellow is harmless. just the Mellin transform of CC infinity function. But this guy is going to have poles, and the residues of the Eisenstein series. Okay, so you see, Eisenstein series is a variable of is a function of two variables z and s. So if you take a residue in s, what remains is still a function on z. Okay, those residues are going to be the Vg of z that I stated in the statement of the spectral theorem several slides ago. Okay, so this is what is going to happen. Okay, so this is what we had written over here. So the point is, one has to study the meromorphic continuation of E of z comma s, and also the poles. One has to study these poles very well. For instance, one has to show that the poles are all between 0 and half. So there will be some residues that are picked up when you shift the contour of integration, and for the rest you can just integrate over IR. Okay, and then so you have gotten some expression for E of z phi in terms of some functions Vj prime of z and this integral. Okay, one has to then show that these functions, residues that you had obtained, are actually in L2 with some estimates, and then you can replace them with their orthonormalization, and then one can show that you see, the point is that one can show that these guys, the Laplacian eigenvalues of these, are all between 0 and 1 by 4. Okay, so I probably won't get time to explain. The Laplacian eigenvalues here are all between 0 and 1 by 4. The Laplacian eigenvalues here are all greater than 1 by 4. And if you have anything like a self-adjoint operator, if you have eigenspaces corresponding to distinct eigenvalues, they are orthogonal. Okay, so essentially this part is orthogonal to this part. So this coefficient, although we don't know what it is, you can recover it as in terms of simply the inner product with Vj. Okay, with the orthonormal projection. Okay, so using some more information about the Eisenstein series, unfortunately I won't have time to talk about it. Using some more information about the Eisenstein series, namely, you have to replace E of zs with E of zs plus, so first of all, in this integral, you have to kind of write it as half times integral over s plus half times integral over minus s. Then you have to apply to what is known as a functional equation of the Eisenstein series, and then use some sort of adjunction. And although you did not know what this m phi of s plus half was that, you could still end up with an integral where you have an inner product between E of dot comma phi, your original pseudo Eisenstein series, and E of dot comma s. Okay, so if you put all these things together, so let me just summarize what we can get from all this. So recall that I defined L2 of H mod gamma cusp, and that was the span of some diagonalizing basis uj, and then span of vj, whatever it is, we call L2 of H mod gamma res. Okay, whenever I say span, I mean closed span. Okay, closure of the span. Okay, one defines L2 of H mod gamma discrete to be cuspidal plus residual. And then the continuous part we define to be the orthogonal complement of L2 of H mod gamma. And what the analysis that we had discussed so far shows is that we can write any f of z in this as this expansion. Okay, so I have skipped a lot of steps over here, but this is what basically that amounts to. And before concluding, let me just state some nice properties of Eisenstein series that were crucial to all these deductions. Okay. Sorry, question? No, okay. We use the fact that the Eisenstein series has a meromorphic continuation. We use that it is holomorphic on real part as greater than half on IR. And then we showed that we assume that we use that it has finitely many poles between 0 and half, all on the real line. Okay, so you did not have to pick up poles anywhere else. And with residue real, positive, and square integrable. And we use the functional equation, and then all of these in turn uses the formula for the constant term of the Eisenstein series. And then, okay, so maybe I should, I'll just remark something about C of S. Whatever the C of S is, it contains the Riemann zeta function in it. Okay? The Riemann zeta function itself has a meromorphic continuation in the functional equation, but you don't need to assume that to prove the functional equation and meromorphic continuation of Eisenstein series. Okay? Rather, once you prove the meromorphic continuation and functional equation of Eisenstein series, you can use that to prove that the Riemann zeta function itself has a meromorphic continuation and the functional equation. Okay, so using that, so when Laplace computed the constant term of certain Eisenstein series, he got new L functions, new partial L functions, which had a meromorphic continuation and a functional equation. Okay, so this can inform number theory quite a bit. Okay, so maybe I won't explain this right, but let me just say that part of the problem is that Eisenstein series are not in L2. So you can't talk of their inner product. But what you can instead talk of is that you can replace the Eisenstein series by what are called their truncations, namely domain of H mod gamma. You can choose a parameter t. Here you consider just the Eisenstein series, which I am denoting by f, and here you replace f with f minus f0. Okay, so this is what is known as a truncation of the Eisenstein series. This function is rapidly decreasing because f and f0 have the same asymptotic behavior as y goes to infinity. So you can ask what is the inner product of truncated Eisenstein series. Though that's actually maybe a bad terminology because here I have put a bar, which means that this is actually bilinear rather than sesquilinear. So the point is one can compute such a thing, and this sort of an expression called Nash-Selberg relations are crucially used in many of the deductions of the previous slide. And this I described only in terms of a fundamental domain, but you can describe this without using a fundamental domain as well. Okay, so I'll be mentioning this in future lectures. But yeah, so next lecture onwards, I'll be discussing L2 of H, G of AF over G of F. Okay. Any questions? Sorry, yeah.
So what about this holomorphic custom?
Sorry?
Holomorphic custom.
Yeah, so you see, so the point is, in this sort of a perspective, I don't know if the spectral decomposition can be captured, but what you can nevertheless do is that you can realize holomorphic customs as functions on GL2 of A over GL2 of Q, and on GL2 of A over GL2 of Q, you have a spectral decomposition. Okay, and these holomorphic customs are very particular kinds of vectors on those customs, or on those cuspidal representations. But other than that, I don't know if a space of holomorphic customs have any other kind of spectral decomposition. Usually, one fixes a weight and a level, and then the space is finite dimensional, and and these are not really even functions on the upper half, on H mod gamma, right? They are functions on the upper half plane which transform in a particular way under gamma. Sorry, I forgot to pause and ask for questions at some point because I
Can we go back to the previous slide?
Yeah,
I wanted
sorry.
to double check.
there may be lots of mistakes. I started.
That CPE, that notation I forgot.
No, so yeah, this was a notation that I wanted to use in. Yeah, so I was thinking of the Borel, but I shouldn't have used this here.
So it is
Huh?
constant term of the Einstein series.
It's a constant term of the Eisenstein series, yeah.
Okay, it's
Yeah.
not you are not multiplying the Einstein series.
No, sorry, my bad, yeah. No, all I mean is I should have written E of dot comma as 0, that's what I
And
tried.
then you said the fact that it is sum of these two terms is and something had good growth and something had bad, and at S equals half something happens. Can you repeat all that?
So this I don't think we S equals half one. So S equals half is mainly for the convergence of E of ZS. When real part of S is greater than half, the expression which defined E of ZS, that thing which you corrected, converges. And then yeah.
If S is greater than half, then this makes sense. And
No, but then by meromorphic continuation, you can make sense of this at other S also.
so again, please. By which meromorphic continuation are you talking about?
Meromorphic continuation in S. So both sides are meromorphic in S. And they agree for sufficiently large real part of S, so they agree on Sorry?
Perhaps that was the comment that you made at some point.
No, that is a comment that I forgot to make.
Okay. Sorry?
Yeah. Because therefore, this is you can use that. You can use that to show that the Eisenstein series is never actual. One of them will be growing faster than y. So integral y times dx dy by y square is y raised to half, right? So then y times dx dy by y square is not convergent.
So it's not in LP.
Yeah.
Why only? One of the two terms will always be good.
Any other questions?